As philosophers, I think we've all spent a lot of time pondering what knowledge actually is, right?
Yeah.
Like we all have beliefs, but what's that extra thing, that special something that turns a simple belief into knowledge?
Yeah, definitely. The idea of justified true belief has been a cornerstone for ages. But, as anyone working in philosophy knows, the tricky part is really unpacking that one word, justified. What does it actually mean for a belief to be backed up by good reasons or evidence?
That's exactly it. And that's where today's deep dive leads us into justification logic, this fascinating world that tries to formalize that justified piece of knowledge. It's like a system that takes that traditional idea of knowledge we're all familiar with and tries to make it super precise.
I think what's really cool about justification logic, especially for philosophers, is that it goes beyond what traditional epistemic logic does. That system with its modal operators lets us talk about what's known or believed across all these different possible worlds, but it doesn't always get into the reasons behind those beliefs.
Right. It's like epistemic logic says, hey, it's known that P, but justification logic wants to go further, right? It wants to make the justification itself a formal thing we can study. Like it's the difference between saying, I know the sky is blue and saying, I know the sky is blue because of how sunlight scatters in the atmosphere.
Exactly. It shifts from just implying something is known, where the idea of knowing just tags onto a statement, to making it explicit. The justification becomes a real part of the logical syntax. We're not just saying we know something, we're showing why we know it.
So for this deep dive, we're going to explore how justification logic does this, how it turns this philosophical idea of justification into something formal. We want to see what it can teach us about epistemology and the big question of what knowledge really is, the stuff at the heart of philosophy. And for those of you following along, we're mainly using the Stanford Encyclopedia of Philosophy's entry on justification logic, which gives a great overview of the field. So let's start at the beginning. Why did justification logic even come about? What were the philosophical problems or questions that led to its development?
The main reason, as we've touched on, is that people wanted a better way to model that classic definition of knowledge, justified true belief, a way that standard epistemic logic just couldn't quite do. While modal logic does a great job with belief, using possible worlds, and truth through factivity, it doesn't really represent justification within the formal system itself.
So it felt like modal logic was helpful, but wasn't capturing all the subtle points that philosophers have always seen as essential to understanding knowledge?
Exactly. And two big intellectual traditions, both important for philosophy, really influenced the development of justification logic. The first, naturally, is the epistemic tradition itself. Thinkers, all the way back to Plato, have stressed how important justification is for separating plain belief from knowledge. And of course, the whole Gettier problem really showed that just having a true belief, even if you got it through some kind of reasoning, isn't enough. The kind of reasoning, the justification, is crucial.
Right, those classic cases where someone has a true belief, but their reasoning is flawed or based on luck.
Exactly. And within this epistemic tradition, people started to realize that modal logic, with its focus on truth across all possible worlds, saying knowledge is truth in every accessible world, was missing something. Justification, on the other hand, seemed to be more about an existential claim, saying knowledge happens when there is a good justification or reason for the belief.
That makes sense from a philosophical point of view. Instead of getting lost in the idea of truth in every possible world, justification logic brings us back down to the specific reasons we have for what we believe. What was that second tradition that had a big influence?
That was mathematical logic, specifically the intuitionistic kind. For a philosopher who wants to understand the foundations of knowledge, intuitionistic math is really interesting because it says that mathematical truth comes from the existence of a proof. This is the whole idea behind the Brouwer-Hating-Kolmogorov BHK's semantics. According to BHK, you can only say a mathematical statement is true if you've got a constructive proof for it.
So in this mathematical world, a proof isn't just showing that something's true, it makes it true. It becomes a specific type of justification.
Exactly. And justification logic takes this idea and runs with it. It treats proofs not just as strings of symbols, but as actual objects that have structure and can be manipulated and combined. A key figure here was Kurt Gödel back in the 1930s. He was trying to figure out how to translate intuitionistic logic into the classical modal logic S4, essentially by sticking a provability operator in front of every subformula.
Interesting. So Gödel was already hinting at a link between proofs and knowledge or belief, the way modal logic captures them.
Right. He didn't quite manage to define intuitionistic logic purely in terms of classical provability, and of course he had those famous incompleteness theorems that mess things up. But later on in a public lecture, he said that thinking about explicit proof statements like it is a proof of F could be a really good way to understand his provability calculus S4.
And this idea of explicit proofs, making the reason why clear, is where justification logic comes in, especially with Artemov's logic of proofs.
Yeah,
LP.
exactly. Sergei Artemov took Gödel's idea and really formalized it, treating proofs as these concrete justification terms with specific operations. So it's a fascinating interplay. The philosophical problem of justification in epistemology meets the study of proof in math, and out pops justification logic.
Okay, we've got the philosophical motivation and the mathematical logic motivation. Now let's talk about hyperintentionality. Philosophers are pretty familiar with intentional contexts. What's hyperintentionality, and how does justification logic help us deal with it?
The concept of hyperintentionality, which Creswell's paradox really highlights, shows a big problem for any account of belief or knowledge that's purely based on truth conditions. You could have two statements that are logically equivalent, meaning they're true in all the same possible worlds, but someone might believe one and not the other.
That's a big part of philosophical discussions about belief and understanding. Like you said, someone might believe a simple tautology but not realize it's the same as a much more complex logical truth. They seem different, even if their truth value is the same in all possible worlds.
Exactly. If we think of statements as just sets of possible worlds, then logically equivalent statements become the same thing. This creates a problem when we're trying to understand belief, knowledge, and other contexts that are affected by how a statement is expressed or understood, not just whether it's true or false. These situations where swapping logically equivalent things doesn't necessarily keep things true are called hyperintentional.
So how does justification logic, with its focus on justifications, solve this?
By keeping track of the justifications behind beliefs, justification logic inherently considers the syntactic form of those beliefs, the underlying reasons. The justification term gives us more detail than just whether F is true or false. It lets us tell the difference between beliefs and logically equivalent statements based on what justifies them.
Can you give an example that would resonate with a philosopher?
Think about a really complex math theorem, like Fermat's last theorem, and compare it to a simple statement, like 0, 0, 0. Mathematically, they're both provable, so they're logically equivalent, true in the same mathematical structures. They're the same statement in a possible worlds framework. But the proof for Fermat's last theorem is super complicated, while the proof for 0, 0 is trivial. In justification logic, a justification for 0, 0 would be simple, reflecting that easy proof. A justification for Fermat's last theorem, if we could even write it out, would be super complex, just like its proof. So even though the base statements are logically the same, justification logic can tell them apart by looking at the nature of their justifications, which is important when we're talking about knowledge or belief that's based on having a proof.
So traditional modal logic might say they're interchangeable, but justification logic, by looking at the justifications, recognizes the difference in how we know those two truths. That's a really powerful tool for analyzing philosophical ideas about understanding and belief. This gives us a good grasp of why justification logic is so interesting for philosophers. Now let's look at how it works. What are the basic building blocks of this system?
The core idea is that justifications aren't just abstract notions. They're abstract objects with a specific structure, and they can be combined and manipulated. Like we talked about, formal proofs in math are a good example of this.
And the key piece in justification logic is TF. We love analyzing notation. What does this formula mean?
Yeah, it's read as a justification for F. It's important for philosophers to know that justification logic itself doesn't try to give a complete philosophical definition of what it means for justify F on a metaphysical level. It's more about setting up formal rules for how justifications work, similar to how propositional logic deals with connectives without defining truth itself.
So it's more about the formal rules than a deep philosophical theory of justification.
Right. And it usually builds on classical propositional logic, which is great for truth-functional reasoning. This lets justification logic tackle a lot of standard philosophical examples about knowledge and belief. It can handle things like Russell's example, Goldman-Kripke scenarios, and Gettier-style problems, all within a basic logical framework. And unlike some epistemic logics, it doesn't assume that justifications are always factive, so TF doesn't automatically mean S is true. This lets us model beliefs where the reasons, even if they're genuine, might be wrong.
You said justifications have operations. One is application. What's the idea behind it, and how do you write it formally?
The application operation, written as, is all about reasoning. The idea is that if you have a justification for A, then B, A right error B, and you have a justification for A, then you can apply S to get a justification for B. This is like modus ponens, but for justifications. Formally, it's the axiom. S here, right arrow B, right arrow.
Makes sense. If your premises are justified and lead logically to a conclusion, then that conclusion is also justified. It's like the modal logic axiom for how knowledge works with implication. Box A, right arrow, B, exactly. But the modal version has that problem of logical omniscience, where it says an agent knows all the consequences of their knowledge, even if they haven't thought about them. Justification logic application operator lets us track how we get the justification for B from the justifications for A, right arrow, B, and A.
And that's why justification logic can handle puzzles like the red barn example differently, right? How does it work with that? Yeah, that's a good example. Remember, you're driving through a place with tons of fake barns that look real. You see a barn-like thing and think it's a barn. Now, even if it happens to be a real barn, you don't really know it's a barn because your justification, it looks like a barn, isn't reliable there. But if you notice it's red, and there are no fake red barns, you might know it's a red barn, which means it's a barn. The problem is, you seem to know something. It's red, that implies something else. It's a barn that you don't know.
So how does justification logic make sense of this?
Your initial justification for the barn belief is, so it's UB, B for barn. With all the fake barns around isn't enough for knowledge. Now you see it's red and have the belief V, B wedge, red barn, and we say V is knowledge. No fake red barns. We also have a justification for red barn implies barn, so A, B wedge, R, right or B. Using application, we get G.BB.
So you have a new justification for believing it's a barn based on knowing it's red and knowing the logical implication.
The point is, it's AU.VB. Not that your original is suddenly knowledge. Your initial belief might not be knowledge, but your knowledge of the red barn, plus logic, gives you a different justification for believing it's a barn, and this one can be knowledge. Justification logic can track how justifications change, which modal logic doesn't always do well.
That really shows how justification logic can address tough philosophical problems by being explicit about the reasons behind our beliefs. Now, there's also the sum operation. What's the idea behind that?
The sum operation, written as S plus T, is about combining evidence. If your justification for F, then having another justification doesn't make less valid. And if T justifies F, then S plus T also justifies F. We write this as SF right arrow S plus TF.
It's like saying that having one good reason to believe something isn't made worse by having another reason, even if it's redundant.
Exactly. Think of S and T as different pieces of evidence for the same conclusion. If S alone is enough to justify F, then adding T on top of it should still justify F. In the logic of proofs, S plus T is like putting two proofs that show the same thing together.
Okay, so we have application for logical implications and sum for combining evidence. Now we've got basic justification logic. What's important about this for philosophers?
Maths is like the simplest version of justification logic. It's got classical propositional logic, the application axiom, and the sum axioms. From a philosophical viewpoint, it's interesting because it represents a totally skeptical agent, someone who needs an explicit derivation to accept anything is justified. And you really can't prove any statement like TF directly.
So it's a framework for thinking about justification, but it doesn't assume anything is justified to start with. Not even logical axioms. That's serious skepticism.
True, but isn't useless. It lets you derive relative justifications. You can prove things like, if X justifies A, Y justifies B, and so on, then T justifies F. It's a starting point where you can add principles or assumptions about what's initially justified.
It's like setting up the rules of a game before deciding on starting positions. Now, what about logical awareness and constant specifications? Those seem important for understanding how real people reason.
Definitely. Logical awareness is the idea that logically true things, like the axioms in our system, are justified just because they're logically true. But that's an idealization. Justification logic uses constant specifications to model different levels of logical understanding.
So instead of assuming everyone's perfectly logically aware, we can represent agents who understand and can justify some logical principles, but not others.
Precisely. Justification constants like C, represent basic justifications for axioms that we just accept in a given context. A constant specification, CS, is a set of formulas like CN-LC1A, where A is an axiom and C1 are constants. So it's not just that A is justified by C1, but that this justification might itself be justified by CO and so on, showing different levels of awareness.
So the length of that chain of constants for an axiom tells you how deeply someone understands the justification for that axiom.
Exactly. There are different types of CSs. An empty CS means you got a totally skeptical agent using just. A finite CS means you assume a limited set of justifications, which is more realistic for how people think.
What about axiomatically appropriate and total CSs?
Axiomatically appropriate is key for internalization. It means that for every axiom, there's at least a basic justification in the CS, and if you have a chain of justifications, you can always make it longer. It's a kind of recursive awareness. A total CS, PCS, is the strongest one. It includes every possible chain for every axiom, representing a perfectly aware agent.
Okay, so CSs let you customize the logic to show different levels of logical awareness. How do they relate to math's FJ?
Math is what you get when you take and add all the formulas in a specific CS as axioms. Its only rule is modus ponens, plus a rule called axiom internalization. This rule lets you infer CN1A for any axiom and any string of constants. It's like saying you can always justify an axiom and justify that justification and so on. The logic with a total constant specification.
And you've mentioned internalization a few times. What is the internalization theorem and why is it so important?
Internalization is a key property of justification logics. It's about the logic being able to reflect on its own proofs. The theorem says that if you can prove F in the axiomatically appropriate CS, then there's a justification term made from the constants in the CS and the logic's operations, so that you can also prove in that logic.
So if you can prove something in the logic can prove that there's a justification for it. That's pretty self-aware for a logical system.
It is. You usually prove it by induction on the length of the proof for F. If S is an axiom, then the CS gives you a P, where it is also an axiom. If F comes from modus ponens, you use the inductive hypothesis and the application axiom to get st.tFFF. It shows that the logic can represent the justifications for its own theorems.
This is different from modal logic, where you just have the necessitation rule. If F is provable, then box F is too. Here, the justification is part of the formula itself. Okay, now how do you extend this basic framework to deal with more complex epistemic concepts?
You can extend in math's F's JCS, which are close to the modal logic, to create explicit versions of other stronger modal logics. This is done by adding new operations and axioms.
Earlier you said that factivity can be captured with just an axiom. Can you explain that?
Yeah, the factivity axiom is TF right arrow F. If T justifies F, then F must be true. It's like the truth axiom, box F right arrow F, in epistemic modal logics.
And adding this to MathsEc gives you a MathsF JT which deal with justifications that guarantee truth.
Right, they're meant to model strong justifications, like mathematical proofs. But even a true belief with a good justification might not be knowledge, as Gettier showed. Factivity alone doesn't solve all the problems.
Right, it's complicated. Now, what about introspection? How does justification logic handle positive and negative introspection?
Positive introspection, the idea that if you know something, you know that you know it, is a big deal in epistemology. In modal logic, it's box F, right arrow, box S. Justification logic uses a unary operation. If T justifies F, then justifies the fact that T justifies F. This is the positive introspection axiom, TF right arrow. So F is like reflecting on your justifications. If T is your reason for F, then your reason for thinking T is a good reason for F.
You could say that. T is like a certificate for T. Think of peer review. A reviewed paper, F, has its claims justified by its arguments, validated by the referee's report, argument. Adding this gives you logics like math's FLP, and with the factivity axiom, you get the logic of proofs, which is connected to the modal logic and the idea of mathematical proof.
Is especially important for philosophers because of its strong introspective features. What about negative introspection? The idea that if you don't know something, you know that you don't know it. Negative introspection, written as neg box F right arrow box neg box F in modal logic, is more controversial. In justification logic, it uses another operation. If T does not justify F, then justifies that fact. This is the negative introspection axiom. Neg F, right air. Neg T.
This seems trickier. How can you justify not having a justification?
It is. Positive introspection is about verifying existing justifications, but negative introspection raises more questions. For formal proofs, it's hard to imagine a general method that would always justify neg TF for every F that doesn't justify. The operation was one of the first things in justification logic that went beyond thinking of justifications as just abstract proofs, suggesting it can model more general types of reasoning, including reasoning about what we don't know.
So justification logic can explore systems with negative introspection even if it's philosophically debated.
Yeah. By adding and its axiom, you get logics like maths, rea forti, and math, which are like the modal logics. And
This shows how flexible justification logic is. It can handle a lot of different epistemic principles. Now, what about Geach logics? What are they and how do they fit in?
Geach logics are a huge family of modal logics, named after Peter Geach. They have axiom schemes called Geach schemes, which are generalizations of an axiom Geach proposed. The important thing is, this family includes loads of standard modal logics like maths FT, S4, and many more. These axioms often relate to interesting properties of the accessibility relations in possible world semantics.
And the amazing thing is that even these general modal logics have counterparts in justification logic.
Yes. A big accomplishment in the field was showing that for basically every Geach logic, there's a corresponding justification logic that's related to it by a realization theorem, which we'll talk about later. This often involves adding new function symbols to justification logic and new axioms to control those functions, mirroring the Geach logic's axioms. For example, the counterpart to needs two new function symbols and a specific axiom scheme. While the meaning of these new symbols isn't always as clear as application or sum, the formal connection is strong. This makes justification logic much broader, showing it can provide explicit foundations for a wide range of modal systems.
This really emphasizes how powerful justification logic is as a framework. Now let's talk about how we give meaning to these systems, the semantics of justification logic.
The most common semantics, mainly developed by Melvin Fitting, builds on Kripke's possible world semantics for modal logics, but adds things specifically for justification terms.
So we still have possible worlds and an accessibility relation, but we need something extra for justifications.
Right. You have possible worlds, an accessibility relation, a valuation function for truth values, and an evidence function. This function takes a term and a formula and outputs a set of possible worlds. The idea is that if world gamma is in that set, then T is seen as relevant evidence for gamma. It's important to note that relevant evidence here doesn't mean it guarantees truth. It just means T is seen as a reason for X in that world.
So how do you know if TX is true at a world?
It has two parts. First, must be true in all worlds accessible from gamma, like in Kripke semantics. Second, Tx is true if gamma is in the set, so Tx is true if is believed and is a relevant justification for it in that world. This lets you have situations where someone believes something but doesn't have a justification for it, or where they have a justification that's not relevant in their current state.
And what about operations like application and sum? How do they work in this semantics?
There are conditions on to match the axioms for application. If S is relevant evidence for X right arrow Y at gamma, then E dot T must be relevant evidence for Y at gamma. You write this as SS X right arrow Y ats, the subsatec math T for sum. If S or T is relevant evidence for X, then S plus T is also relevant evidence. Mathkek mathgans S lexcam. S plus T X.
What about constant specifications? How do you make sure the models respect the assumed justifications for axioms?
A model meets a CS if for every CS the ES, the evidence function makes sure math ECX includes every world in the model. This means those basic justifications from the constants are always relevant.
So this ensures the models respect the starting assumptions in the CS. Now what about completeness? Do the justification logics capture everything that's valid in these models?
Yes. We have a completeness theorem that says a formula is provable in if and only if it's valid in all models that meet the CS. This is weak completeness. Interestingly, the proof for math CS is often easier than the one for basic modal logic.
You also mentioned weak and strong completeness and fully explanatory models. What's the difference, and what do they mean for justification logic?
A model is fully explanatory if, whenever is believed at, true in all accessible worlds, there's a justification where it's true at. Strong models are ones that are fully explanatory. Strong completeness means everything valid in strong models meeting a CS is provable. It's harder to get than weak completeness and relates to internalization. If the CS is rich enough, axiomatically appropriate, you can get completeness with respect to strong models. The proofs often use techniques similar to modal logic, and these models can also be used to prove the realization theorem, which connects justification logic back to modal logic.
It seems like these different approaches to semantics give us a good understanding of justification logic. You also mentioned single-world justification models and ontologically transparent modular semantics. What are those?
Single-word justification models are interesting because they're simpler. There's only one world, and the evidence function just says if is evidence for in that world. Surprisingly, a lot of justification logics are complete even with these models, suggesting that the accessibility relation can be captured by the evidence function. These models have been really useful for proving decidability, like Mikurtyshev did for MathCFLP, and for figuring out complexity and conservativity.
That's amazing that you can do so much with just one world. What about the modular semantics?
Modular semantics, or ontologically transparent semantics, tries to clarify what justifications actually are. Statements are still true or false, but justification terms are interpreted as sets of formulas. In a single world, you have truth values for atomic statements. Then, justification terms are sets of formulas with specific conditions. For example, the set justified by S, E, die T has to include any F where there's a G, so the G right arrow F is justified by S and G is justified by T, and the set justified by S plus T has to include everything from either S or T.
So a justification isn't something in a world, it's a bunch of statements in the language.
Right. Statements have semantic meaning, truth values, but justifications have syntactic meaning, sets of formulas. This makes things hyper-intentional because even if F and G have the same truth value, TF and TG might be different. It justifies F but not G. It lets the semantics tell apart justifications based on their syntactic form. This has been used to prove soundness and completeness for various justification logics.
This gives us a good understanding of how justification logic can be interpreted. You also mentioned connections with awareness models. What are those?
Awareness models were introduced in epistemic logic to deal with logical omniscience, the idea that knowing some facts automatically means knowing all the consequences, which isn't realistic. They add an awareness function to Kripke models, specifying which formulas the agent is aware of in each world. You only know something if it's true in all accessible worlds and you're aware of it.
So you have to be aware of something to know it, even if it logically follows from what you already know.
Right. The connection to justification logic is in how the truth condition for TF works. It's true if F is true in all accessible worlds and is admissible evidence for F. So awareness and admissible evidence play similar roles, both trying to give a more nuanced view of knowledge. But justification logic, through its operations and conditions on the evidence function, makes evidence have a logical structure that's often missing in awareness models. In a way, justification logic provides a more principled way to model limits on knowledge. Some research even looks at math's FLP, where justification terms are agents or actions, connecting it to awareness and group knowledge.
That's an interesting link between different approaches. Now, what about realization theorems? What do they tell us?
Realization theorems connect justification logic back to epistemic logic. The idea is that TF in justification logic gives an explicit basis for box F in modal logic, which sort of means there's some justification for F without saying what it is. Realization theorems make that implicit justification explicit.
So you take a modal logic statement about knowledge and rewrite it in justification logic by actually providing the justification.
Exactly. You use a forgetful projection to change into box F, giving you... So you can do this with whole logics too.
And then the correspondence theorem tells us something important about these projected justification logics and modal logics.
Yes. It says that when you do this projection with certain justification logics, you get the matching modal logics. For example, projects to maths for math. This shows a strong connection between these two types of epistemic logic.
Wow. It seems like modal language for knowledge might just be a shorthand for talking about justifications. But what does the realization theorem actually say?
It goes the other way. It says that if you can prove F in a modal logic, like Mascou's, there's an algorithm to assign justification terms to the box operators in F, so that the new formula is provable in the matching justification logic, like Mascou's. This often means using variables for negative occurrences of box, which fits the existential reading of the modality, means there's a justification for F.
So if you can prove